Hello, Malcolm, chemistry students. So today's example, not really a lesson, more of an example, is about the common ion effect. And we have done one or two examples prior to this that are similar. So nothing too new here, just going to review a bit and then look at a specific type of example. Okay, so to begin, we're given a scenario here. So imagine we have some sodium chloride already in a solution, right? So we have aqueous sodium chloride at a certain concentration. Okay, not really too worried about the quantities here, just we already have some sodium chloride present. Now, if we were to drop some silver chloride into it, we would actually see that the expected solubility would end up decreasing because we already have what's called a common ion. Look, between silver chloride and sodium chloride, we see that there is a similar common ion here, the chloride ion. It's the presence of this ion that will decrease this solubility, and we'll get to why in just a moment. Okay, but this is an example of a common ion existing between two solutes, thereby decreasing solubility. So you can think of this, maybe to help you understand this better, you can think of it as the Chatelier problem. So if there's already chloride in the solution, the equilibrium will shift to which direction? So let's think of it this way. Think of it as a stress. If you increase the concentration of chloride ion, that's right here, increasing the concentration of your chloride ion, that's going to then move this equilibrium, it's going to shift it more to the, hopefully you're thinking the direction is left, right? It's going to shift it more to the left because you're increasing this concentration. So instead of it increasing solubility, it is not going to do that. It's going to move to the left to increase precipitation or crystallization, okay, thereby decreasing solubility. Okay, let's move on. Want to mention this because we're going to be using KEQ especially, well, KEQ, only KEQ in the next set of examples. So whenever you're going to write a KEQ expression or Q expression, your reaction quotient or your solubility constant in this case, you would need to include all sources for all relevant ions. Okay, moving on. So in this example, it's asking us to calculate the molar solubility, which really means the concentration at saturation. So I know in the last slide I said I referred to Q. Now, we're not really going to need to do that because the question is asking us for concentration at saturation. So we don't need to worry about Q. It's not asking us that kind of question. Here we're worried more about KEQ, but because it's a heterogeneous solutions, it's about a solute and a solvent. We're actually going to more specifically look at KSP, right? Okay, so here are three situations. We have copper chloride dissolving in water. Now, given this KSP, notice it's quite low. All right, so our three situations are water, then our second one is sodium chloride. Now look at sodium chloride. Here we have a common ion. Here we have a chloride, and here we have a chloride. Right, so there's already a certain amount we have to take into account of our common ion, in this case chloride. In our third situation, we have a common ion as well. Instead of it being chloride, though, it's a solution of copper 1 sulfate. So here we have copper and copper. Right, so three different situations, and two of them we have two different situations of common ions. Okay, and again we have our KSP. I'm going to switch screens now so we can start to solve this. Okay, so beginning with A. All right, let's rewrite our dissociation. Copper 1 chloride. Okay, copper and chloride. We know that these are aqueous. Okay, I'm going to show this in this first example. I'm going to show you how to do it using an ice table. There is a bit of you'll see. There's a bit of going back and forth here because we're not really calculating all of these, or you'll see. Okay, so let's start filling things in. Okay, we know that because this is a solid, we don't include any of this. We know that at time 0, we have no concentration, right, in water especially. So it will change according to its balanced ratios mole ratios by these values x. So we add I and C, and we have XX. So now that allows us to write our KSP. All right, so KSP expression is Cu. That's a Cu. Okay, Cl. Good. We have XX. We know the value for KSP. That was given to us in the question. So let's just write down what's given to us. Okay, back to solving. All right, so 1.7 times 10 to the negative 7. We know that we're going to root both sides to solve for x, and here we are. Okay, I like to read left to right, so I'm going to write just a preference. X is then equal to 4.1 times 10 to the negative 4. We know that this is concentration, so it's that. All right, so we're not completely done yet. We do have to say that, and this is where I was referring at the beginning, hopefully I didn't confuse you, but you do have to, you can use a nice table, but you've got to kind of go work backwards or think of this in the reverse direction. Considering then going from 1 mole, fortunately this is all 1-to-1, but 1-to-1, right? So if we know the value of x, which we now do, in either case it's 1-to-1, so it doesn't matter, but we know the value of x, and we know that it's in a 1-to-1 ratio. So whatever value for concentration we get for copper or chloride, since it's all 1-to-1, we know that the concentration then of copper 1 chloride is going to be the same value. Okay, so that concentration is going to be the same because it's 1-to-1. So we can therefore say, concentration of CuCl is 4.1 times 10. I was going to write 7, almost did, times 10 to the negative 4. Okay, so even in just water itself, it's not too soluble. Right, let's scroll down to answer B. So different situation. Okay, different situation here. It is that we now have a 0.10 mole per liter concentration of sodium chloride, where chloride is our common ion. Now, given that ice table above, right, given these values at equilibrium x and x, specifically for chlorine here, chloride there, we need to add that extra amount. Now we know that sodium chloride is going to dissociate in a 1-to-1 ratio, and we're given the concentration of this at 0.1. Now, fortunately, it's all a 1-to-1 ratio, so we know that we're going to have this concentration of chloride ions. Okay, that means our original ice table, that value at equilibrium is not just x. That means it's actually x plus 1. Okay, so our KSP is going to look a bit different. Now I'm still using that original ice table there, so I'm just going to rewrite our KSP. It still is copper and chloride. That expression doesn't change, but what's changed here is for Cl, it's no longer just x, but it's x plus 0.1. Okay, we know what KSP is, 1.7 times 10 to the negative 7. So we can solve for this, or, well, we are going to continue to solve for this, but we can say something that might help us out. We can say, since the hundreds rule, I was going to say is follow, but I'll just write applies. Since the hundreds rule applies, therefore we can cancel x. All right, now that's referring to specifically this x, right? Not going to cancel this x because that wouldn't make mathematical sense, you're going to cancel this x. What we're saying really is that this quantity here is not, that change is not sufficient enough or significant enough. What is instead is this value here. You can double check by doing this question without that assumption, and you'll see that you'll get the same answer. So that makes this question a lot easier, right? So we just get 0.1x is equal to 1.7 times 10 to the negative 7. And so we're going to just divide both sides by 0.1, and we get x is equal to 1.7 times 10 to the negative 6 moles per liter. So again, just like the last question's ice table, we have a 1-to-1 ratio. If we know the concentration of one of these ions, we know therefore the concentration of copper 1 chloride. So we should write therefore the concentration of copper 1 chloride is 1.7 times 10 to the negative 6 moles per liter. Okay, now let's compare 1.6 times 10 to the 6 to the previous concentration just in water. Now this should make sense to you. In water, it was more, the concentration was greater, right? We could dissolve, therefore we could dissolve more copper 1 chloride. In the presence of a common ion, it is less, right? 1.7 times 10 to the negative 6. Okay, last scenario here. All right, so this is C. So C had a common ion as well. The difference, though, is that this common ion is not chloride. The common ion in this case was copper. Okay, and the situation was this. We had 0.01 moles per liter of copper 1 sulfate. Okay, now copper 1 sulfate dissociates like this. Okay, and we know that it's a 0.01 molar concentration. Because of that 1-to-2 ratio, we're going to multiply this by 2, so it's actually going to be 0.02. And sulfate is 0.01, but we don't really care about this. It's a spectator here. Okay. So now we know how much copper is present, and remember copper is our common ion in this case. So we're going to do the same thing we did in the previous example where we had chloride as our common ion. We know that our KSP expression, the expression itself doesn't change, it stays the same, right? Copper and chloride. But because copper here has an added value, what we're going to do is it's no longer just X, we have to add that 0.2. Not 0.1 because it's a different mole ratio, but 0.2. Chloride stays the same at X. And we know that KSP given to us is this. Okay, so also that same assumption applies. So since the hundreds rule applies, therefore we can cancel X. Okay, this X, right? Okay, so what we end up with is 0.2x and 1.7 times 10 to the minus x, right? Divide both sides by 0.2 and we get that x is equal to 8.5 times 10 to the negative 6. Okay. Good, and going back, since we know what X is, going back to the original ice table, again, it's a 1-to-1 ratio. We know what X is. We therefore know what the saturation of copper, what the molar solubility of copper 1 chloride is. So therefore, the concentration of copper 1 chloride is 8.5 times 10 to the negative 6 moles per liter, or big M. Okay, again, this is lower than, just to double check your work, 8.5 times 10 to the negative 6 is lower than it was when it was just in water. So that should make sense because it has a common ion. All right, so let's go back. Right, we've answered these questions. student in the past, this is exactly what he said. To quote him, there you go. I thought that makes sense. I know other students have said something similar. Okay, so here are your home fund questions to work on. Page 471, questions 7, 8, and 9. Not too many here. Post questions as you normally do. I hope this helps.